Let's talk about logarithms in this section. So we're going to be taking the derivative of logarithms, and we've already been taking the derivative of exponential functions. So whenever we look at these in this section, I'm wanting you to remember, if you have something like y is equal to the natural log of x, we know natural log is understood to be log base e. Any logarithm, it is literally asking you, what number do you have to raise that base to get the number on the end? So this is asking you, what power of e do you need to raise it to get to an x? And you already have the answer over here. So this in exponential form would be e to the y power is equal to x. So now, let's go ahead and talk about the derivative of that. If I start off with a proof here, I want to prove that the derivative with respect to x of a log function base b. We'll go ahead and do the general case. It's the hardest derivative, but if we get this one, they'll all fall right into place. So I want to show that the derivative of log base b of f of x is equal to f prime of x over f of x natural log of b. Okay. So I'm going to start off the proof by just letting y equal log base b of f of x. So I know that dy dx better be able to equal this up here. Okay, so I can't leave the log base b in there and try to take the derivative, otherwise I'd have to be using that derivative formula. I get rid of the log base b by doing the inverse of a log base b on both sides. So you'll see I exponentiated with exponential base b on both sides of the equation. Exponential base b, log base b are inverse functions. They eliminate each other, and you just have the f of x on the right. So now I have b to the y is equal to f of x. At this point, we take the derivative implicitly. The derivative of every single exponential function in existence is that exponential function times the derivative of its exponent times the natural log of its base. Okay, so I have all of that in there. Now I need to take the derivative of the right-hand side. That's a lot more straightforward, just f prime of x. Now you're supposed to solve for dy dx. So dy dx is being multiplied by the exponential function b to the y and the logarithmic function natural log of b. So I just undo that by dividing them on both sides. So you'll notice I have dy dx is equal to f prime of x over the exponential function b to the y times the natural log of b. And then I can say, please go back earlier in the problem and notice the exponential function b to the y is equal to f of x. So I can substitute that in its place. And I have shown that dy dx is equal to the derivative of what's inside the logarithm, f prime of x, divided by what's inside, f of x times the natural log of b. QED, done with that proof. Isn't that a nice one? Now, as a corollary to that proof, we can talk about easier logarithmic derivatives. If I just have the derivative with respect to x of the natural log of x, you simply just say it's 1 over x. We know it's just 1 over x because the only other thing you could do would be to say, well, can I multiply by the derivative of what's inside? But that would just be a 1. And natural log is automatically log base e, so there'd be no point to multiply by the natural log of e down here. That's just multiplying by 1. So anytime you have just the natural log of x, every time it's just 1 over x. If it's the natural log of f of x, we just say, well, it's 1 over f of x. And this comes from the chain rule, times the derivative of the inside. So we say, well, that'd be f prime of x. And we see our f prime of x over f of x, which was a component in what we proved up here. The only thing it doesn't have, again, is the natural log of the base, because the base would be understood to be base e in this case, and the natural log of e is 1. So now, when I look at some examples here on the next page, let's say I want to find the derivative for the following functions, and I have x natural log of x, and I can say, well, x natural log of x, that's a product. I wanted to make sure you saw that it was a product, so I put the two parentheses beside each other. Product rule says, well, derivative of the first, derivative of x is 1, times the second, natural log of x, plus the first, x, times the derivative of the natural log of x, 1 over x. So this is going to give me natural log of x plus 1 there. And then I go to my next problem, and I can say, well, okay, now it's the natural log of the secant of x. Derivative of any logarithm is 1 over what's inside the logarithm, and then times the derivative of what's inside the logarithm. I need to put a derivative mark on that. And so now the derivative of secant would just be secant x tangent x, but then that's divided by the derivative, that's divided by the original inside the secant x, and I can see that the secants cancel out, and this shows you that the derivative of the natural log of the secant of x is simply the tangent function. That comes in handy in the next class because we'll be talking about the integral of the tangent function works backwards to be the natural log of the secant of x. Now, on down here, what if I have a polynomial on the inside? No big deal, guys. These problems cannot be hard. You just say derivative of every single logarithm in existence is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. Derivative of what's inside, I'm just using the power rule on each term. I would get 12x to the third minus 2. That term goes in the numerator all over that denominator, and you don't even need to factor or simplify or anything like that. That answer would be fine. In the next one, there is a logarithm as a part of this problem, but you need to keep in mind this time the logarithm is the inside of what happens in the function. You can't worry about that logarithm to begin with. You have to worry about the outside of that group. And so I can say, well, this is a composition of functions. I'll have to use the chain rule. 4 is going to have to come down in front times the group to the third power times the derivative of the inside. Derivative of 6 is 0, but the derivative of the natural log of x is 1 over x there. So now I can say, well, my answer is going to be 4 times the group 6 plus natural log of x quantity cubed all over x. Final answer there. Now, whenever you have something like this here on the next page, this is where I'm just trying to get you to see, instead of doing what I did on the previous page, which is fine. So on the previous page, I always said 1 over what's inside times the derivative of what's inside to emphasize the fact this part comes from the chain rule. But rather than showing that out each time, why not just go ahead and say, put whatever's on the inside in the denominator, put the derivative of what's inside in the numerator. It's a quick way to do it. So that's what I'm trying to emphasize on this page. Yes, you can say that the derivative of a logarithm is 1 over what's inside times the derivative of what's inside, but that derivative of what's inside always goes into the numerator. And so now if I have something like the natural log of x squared plus 3x minus 5, you'll see down here in my instructions I say put the argument of the logarithm in the denominator. Okay, x squared plus 3x minus 5 goes down there. Now the derivative of that goes in the numerator. Derivative would be 2x plus 3. Done. If I say something like the derivative of the natural log of the sine of x, you say, well, okay, I put what's inside in the denominator, sine of x. The derivative of sine, cosine, goes in the numerator. And of course that can simplify to be our cotangent function. Now, our logarithmic properties that I just need you to recall is that the change of base formula, if you have the log base b of a, that's equal to the natural log of a over the natural log of b. Cancellation properties, these come up these become helpful especially when you're solving equations. I know that the natural log of e to the a is just a because natural log and e eliminate one another. Same thing here. If I have e raised to the natural log, those again eliminate one another, and you're just left with the whatever the variable a is in this case. So e and natural log eliminate each other. If you have the logarithm inside of an exponential function, they undo one another. Or if you have an exponential function inside of a natural log, they undo one another. Now, our laws of logarithms that you're supposed to remember, if you have a product inside of a logarithm, you can break it apart as an addition. If you have a quotient inside of a logarithm, you can break it up as a subtraction of separate logarithms. And then if we have a power inside of a logarithm, that power can come out in front. Now, I've seen so many students can get that confused. They'll think they're taking the derivative, because normally when we take the derivative of a polynomial, we'll bring the power down in front. So when they do this property of logarithm to expand out and bring that power in front, they'll mistakenly think, well, I've already taken the derivative. This has nothing to do with taking the derivative. It might make taking the derivative in later steps easier, but that's not the derivative in itself. That's just law of logarithms. Now, to show you that in this problem, I'll use that change of base formula from our first page. What I proved, remember I said here the log base b of f of x is equal to f prime of x over f of x natural log of b. So the very instant you look at this problem here, before I even show my work for it, you should know how to take the derivative of that. You say, okay, he said the derivative of log base b was the derivative of what's inside, which would be 1, divided by what's inside, x, times the natural log of the base. This answer has to be 1 over x natural log of 4. It has to be. Now, in order to see the logic in this case, if I use the change of base formula, I can say, well, the log base 4 of x is equal to the natural log of x over the natural log of 4. And then I can understand that that natural log of 4, that's just a constant. I could bring it out in front of the variable function of x. And I can say that's the same thing as 1 over natural log of x, 1 over the natural log of 4 times the natural log of x. Then at this point you could think of it as the product rule and say, well, derivative of a constant is 0 times the second, and then plus the first, 1 over natural log of 4 times the derivative of the second, derivative of the natural log of x, 1 over x. And then you see, this way we can also see that, yeah, your answer is just going to be 1 over x times the natural log of 4 in that denominator. And so anytime we have the derivative of the log base any value b of x, it's going to be 1 over x natural log of b. Some more problems here. And in this problem, I want to use the law of logarithms to make it easier. The law of logarithms says that anytime we have terms multiplied on the inside there, then we can create separate logarithms added together. I'll use that in conjunction with the power rule of logarithms that says those terms can come out in front of the individual logarithm. So as soon as you look at this, you should see for each factor in here, you're going to have a separate logarithm. We're going to have 1, 2, 3 logarithms. The first logarithm is going to be 2 natural log of x. That's where that comes from. The next one doesn't have an exponent, so just plus 1 natural log of 3x minus 1. The last one here, that square root is the same thing as the 1/2 power. So you'll see I went ahead and said 1/2 natural log of x minus 4. All of these were multiplied, so of course they're all being added. Now that's as far as I can go to expand it out using my law of logarithms. It's time for the derivative. So I said, well, okay, the 2 is going to go along for the ride times the derivative of the natural log of x, which is 1 over x. My second one, derivative of the natural log of 3x minus 1, I know the 3x minus 1 goes in the denominator. The numerator becomes the derivative of 3x minus 1, which is 3. The next one, again, you can think product rule if you like. Derivative of the first would be 0 times the second plus the first, 1/2. Now times the derivative of the second. Derivative of any logarithm is whatever's inside the logarithm goes in the denominator. The derivative of that goes in the numerator. That's why the numerator is 1 here in this case. Now from here to here, all I did was simplify. I'll have 1 over 2x plus 3 over 3x minus 1. And then I just distributed the 2 through this denominator and said that's going to be plus 1 over 2x minus 8. Now, this problem, it wasn't just wanting me to find the derivative. If it were, I'd be done at that point. But this one, it was wanting to know the slope of the tangent line at x equals 1. Okay, well, the slope of the tangent line, all I need to do is plug the x value of interest into my derivative equation. So when I do that, I'll just get 2 over 1 plus 3 over 3 minus 1 plus 1 over, it'd be 2 minus 8 there. That's where all that comes from. I get 2 plus 3 over 2 minus 1/6. That's a minus because the denominator was a negative 6. And then you can see we have a least common denominator of 6, so I went ahead and multiplied the first term by 6 over 6 to get to 12 over 6. Multiplied the second term by 3 over 3 to get to 9 over 6, and this last term was already fine. It already had the common denominator. You see our numerators are going to be 21 minus 1. That's going to be 20 over 6, which reduces down to 10 over 3. We have the slope of the tangent line at x equals 1 at the, for this natural logarithmic function. Now, in this last problem, I could use properties of logarithms to simplify it. I need to make sure you understand when you can use law of logarithms to simplify and when you cannot. So law of logarithms can break up powers, it can break up multiplication and division. However, it can certainly not break up a sum inside of a logarithm. So when I look at this next problem, I need you to see first and foremost, there's no properties of logarithms that's going to help you out here. You just have to start taking the derivative. So that's what I did. I said derivative of any logarithm, you put what's inside the logarithm in the denominator, and then I can say the numerator becomes the derivative of that. Derivative of x is 1. I thought of this as the group x squared minus 1 to the 1/2 power. So I said 1/2 comes down in front, times the group left alone to the negative 1/2 power. I had to subtract 1 from the exponent. Then you multiply by the derivative of the inside. That's where the 2x comes from. Now, from that point, I was just simplifying. From this step to this step, I said I will cancel out the 2 and the 1/2. I have to cancel that. And then I can say that x is going to go into the numerator of this term that has the denominator of the square root here. Because I knew it was the negative 1/2 power, I couldn't put it in the denominator of the overall fraction, but I can put it in the denominator of that individual term within the numerator of the fraction. So now I can say, well, okay, yeah, that looks better, but I don't like having a fraction inside of a fraction. So I cleaned up my answer by multiplying by the square root of x squared minus 1 over the square root of x squared minus 1. Remember, you must multiply by understood ones. That actually really helped out here because then in the numerator it distributed to the first term to give you that square root of x squared minus 1. When it distributed to the second term, it just canceled out that denominator, which is precisely what I wanted, and I'll just have plus x. In my denominator, it distributed to the first term, and I have x on the root of x squared minus 1. And when it distributed to the second term, we know any square root times itself is simply what's inside of it. So it got rid of that square root, and I have a nice format for the final answer to that problem. Okay, now we've been talking a lot about logarithms. Let's go back and talk about an exponential function here for just a second. And normally when we deal with exponential functions, we get so used to dealing with exponential functions base e. So what if I want us to find the equation of the tangent line to a function that has an exponential function base 10? What I'm asking you to recall here, and we've talked about this in earlier sections, and I've put it as a generalization here just as a reminder. So generalization that you're supposed to know is that the derivative of any exponential function base b is that exponential function base b times the natural log of whatever the base is. So I can say, okay, I should be able to use that within this problem now. So I go up here and I can say, okay, if I'm trying to find the equation of the tangent line, I'll need a point and I need a slope. So before I even worried about the derivative, I was just concentrating on the point. We have the x value, the y value is going to be the function evaluated at 3. We get 10 to the third, which is 1,000. So that means the point at which my tangent line is going through is the ordered pair 3, 1,000. Now I need to find the slope of the line that goes through that point, and that's just given by the derivative evaluated at the point of interest. My derivative is super easy here. You just say derivative of any exponential function is that exponential function times the derivative of its exponent, which is just a 1, times the natural log of its base. That's where the ln 10 comes from. And so then you plug in the 3, and of course 10 to the third, again, is going to be 1,000. And I would prefer not to get a decimal approximation. I'd rather leave it exact. I'll just call it 1,000 natural log of 10. So the exact slope is 1,000 natural log of 10. This was my point. You had to plug this information into your point slope formula. So it becomes y minus 1,000 is equal to m, the 1,000 natural log of 10, times x minus x1, x minus 3. You distribute through the 1,000 natural log of 10. Of course, that 1,000 natural log of 10 becomes the slope of your function. It's the coefficient of x. Just to show that the x was not inside of that natural log, I put a parenthesis around the 1,000 natural log of 10. All of that times x. And then I would have minus 3,000 natural log of 10. And then in order to solve for y, you'd have to add the 1,000 to both sides. So that would be my final exact equation of the tangent line. I also wanted to throw in here that if you're looking at the derivative of b to the f of x, this is the chain rule version of that. We talked about it up here too. That if I'm taking the derivative of any exponential function in existence, the derivative contains that exponential function times the derivative of whatever the exponent is times the natural log of its base. Now, that's for exponential functions. Please don't get that confused with what's coming up next. So in this next problem, I'm going to use a technique called logarithmic differentiation. The only thing the technique of logarithmic differentiation means is that I'm going to take the natural log of both sides of an equation before I start worrying about the derivative. And sometimes it's absolutely necessary to do this. Let me explain why in this case. So if I ask you to take the derivative of y equals x to the 5x, please don't mistake that for an exponential function and say, well, hey, is the derivative x to the 5x times 5 times the natural log of x? That would be terrible because it's not an exponential function. Exponential functions have constant bases and variable exponents. This has a variable base and a variable exponent. There are no derivative rules to handle that. So the only thing I can do is use this technique called logarithmic differentiation to handle the derivative process. Here's what I do. So I start off with the original problem, y equals x to the 5x. And I need to understand, I don't have the tools or the ability to take the derivative of it in that form. So I take the natural log of both sides, and I'll just leave the left-hand side alone for now. But now the reason that taking the natural log of the right-hand side helps is because there's that rule of logarithms that says anytime your term inside of a logarithm is raised to an exponent, that exponent can and should be brought out front. So then that 5x, instead of x to the 5x, that 5x now is a product with the natural log of x. So I can say this is much easier to take the derivative at this point. So while I couldn't take the derivative of y, I can take the derivative of the natural log of y. So I do that. From this step to this step, I'm taking the derivative. Derivative of the natural log of y is 1 over y times the derivative of y with respect to x. I move to the right-hand side, and I'm thinking product rule. Derivative of the first, 5, times the second, plus the first, 5x, times the derivative of the second, 1 over x. So now, if I'm trying to solve for dy dx, I need to multiply both sides by y. That's what that right there is doing. And then I simplified my right-hand side. It'd just be 5 natural log of x plus 5, because this x and 1 over x combines to just be a factor of 5 times 1. So I get the 5. Now from this step to the next, what I did is I said, well, now I have a common factor of 5 inside of that group. I'll pull that out front. I did. And instead of leaving y in my answer, I already know what y is equal to in terms of x. It's always better to get your final answer for your derivative in terms of one variable, if you can, and we certainly can in this case. So instead of leaving the y in there, I put what y was equal to, the x to the 5x, brought the 5 out in front, multiplied that x to the 5x, and then what's left over is the natural log of x plus 1 once that 5 is factored out. That's a fun and important problem there. The last one in this section I want to look at, in this problem, you wouldn't have to do logarithmic differentiation. Now, in this last one, I emphasize that is the only way to take the derivative in that problem. Logarithmic differentiation was an absolute necessity. It's not a necessity in this problem, but it sure does help. If you don't use logarithmic differentiation on this one, you would have a pretty hectic change slash quotient slash product rule going on. It wouldn't be too bad, but this way is going to be much easier. And plus, I asked you to use logarithmic differentiation anyway here in the notes. So first of all, if I'm using logarithmic differentiation, I take the natural log of both sides. And because I know that the natural log is going to help me simplify powers, I went ahead and just showed that the square root, it just means that that whole fraction is raised to the 1/2 power, which means every single term inside of that is raised to the 1/2 power. So now when I expand in the next step here, you'll see, well, I have the natural log of y. Please notice every single coefficient of the natural log is a 1/2. It's because all of these were raised to the 1/2 power. So now the first one is going to become 1/2 the natural log of 2x plus 1 plus 1/2 the natural log of 3x minus 7. The next two terms, they're both divided. Well, they're both subtracted. Please remember, anything being divided, whenever you separate it, is being subtracted. So anything in the denominator, you're going to subtract those logs. So I say minus 1/2 natural log of x plus 5 minus 1/2 natural log of 4x minus 3. Now from this point to this point, I'm starting the derivative process. Derivative of the natural log of y is 1 over y dy dx. Derivative of the first term here, I'll have 1/2. Derivative of the natural log of 2x plus 1. The 2x plus 1 goes in the denominator. The derivative of that goes in the numerator. That's why the 2 is up there. Plus 1/2. Derivative of the natural log of 3x minus 7. You see that 3x minus 7 in the denominator. Its derivative, 3, in the numerator. Derivative of the natural log of x plus 5 is just 1 over x plus 5. And the derivative of the last term, the natural log of 4x minus 3. 4x minus 3 goes in the denominator. Its derivative, 4, goes in the numerator. From this step to this step, all I did is I said, well, in order to solve for dy dx, you'd need to multiply by y on both sides. So I did that. And at the same time, I simplified some of my fractions. Here I saw that the 2's would cancel and I just have 1 over 2x plus 1. Here, nothing canceled and I just have 3 over, I distributed 2 throughout that group and got 6x minus 14. Minus 1 over, I distributed 2 through that group and got 2x plus 10. And then minus, 4 over 2 did cancel here, so that's why I have a 2 in the numerator. And then I have my denominator of 4x minus 3. So all of that simplified out, but for your final answer, for the dy dx, it'd be great if you say, well, I know y is that original root. So to get an answer solely in terms of x, you could say I can plug that original root back in there times the expression that I had. And now this is the problem with these logarithmic differentiations. The derivative process is not that bad, but oftentimes the answer that we get is just really long and pretty hard to work with. But it's not hard to get though. Hope this makes you feel better with derivatives of logarithms. Coming up next, my favorite section of the semester, related rates.